Okay, the next one uh, is commonly used by health and safety standard agencies and environmental chemists. So this one is called parts per million, okay, or ppm. ppm stands for exactly what you think it stands for, parts per million, okay? And again, it kind of says what it is right there in the name. So it means in a million particles of your solution, how many of those particles are solute particles, right? So you can imagine, well, why would we use this per million thing, right? If we're saying per million, we must be talking about things that are very, very small, okay? Very, very small concentrations, I should say, because uh, parts per million is a number that we use when, if we were to do, say, a percentage, or to do our other one, our molar concentration that we haven't gotten to yet, we would get numbers that were so tiny. So what we do is we say, okay, yeah, the numbers are obviously very tiny. Let's say how many solute particles there are in a million solution particles so that the number can be not as annoyingly tiny, right? And so how do we do that? Well, we take the mass in grams of the solute, we divide it by the mass in grams of the solution, so that's the total. So again, we're just taking the mass of the solute divided by the total mass of the total solution. That would give us just this part here. So I'm gonna get rid of this in a sec, but just that part there, that would give us parts per one, right? For every gram, 1 gram of solution, how many grams of mass do you have? So parts per one. And that number, if we're using ppm, is going to be stupidly small. It's going to be so small, right? And so the reason we use parts per million is to say, okay, let's just say, we'll say parts per one is going to be stupidly small. Let's multiply by a million, and then we're going to have like 7 instead of 0.0000007. So instead of 0.0000007 grams per gram of grams of solute per grams of solution, we will say we have 7 grams of solute in a million grams of solution. So out of a million grams of our solution, 7 grams of them were solute. Okay, so that's what this part is here. 10 to the 6, type that in your calculator. That's a fancy way of saying a million. Okay, so 10 to the 6 is just another way of saying a 1 with 6 zeros, or a million. And we'll come back to here. Why is it commonly used by these people, by these health and safety standards and the environmental chemists? Well, maybe now it makes sense. Maybe now that we know that it's about things that are very, very small concentrations, it makes sense that it would be these kind of people using it, right? Because if you are an environmental chemist or a health and safety standard agency, you are really, really paying attention to small amounts of things, right? We're looking for things like toxins in food. So we need to be careful. It's not, we can't say, oh, it's 10% mercury in your fish. No, that's not good enough, right? We need to really, really say, finally, things that people are going to be eating, things that are going to be impacting entire ecosystems in the case of environmental chemists. We need to monitor it very carefully, right? Um, if there's runoff from a fertilizer that is getting into waters, that's going to have a huge impact on the environment, as we'll see later in our biology unit, right? So we need to be careful. We need to be on the ball. We need to be looking for very small concentrations. The example here is that 1.5 parts per million. So again, that means if you scooped up a million particles of this water solution, if you took a million particles, only 1.5 of those particles would be fluoride. That's how dilute this solution is, not concentrated at all. Okay, that is the maximum allowable amount in drinking water, right? So you can see we're dealing with stuff in water, things that humans are going to consume, and a lot of humans are going to consume. So that's why they don't play around, right? ppm, we need to be aware of very small concentrations. That's when we would use something like ppm, okay, parts per million. Okay, so now it is time to get some practice with parts per million. Okay, so I'll do some examples. Parts per million, again, all concentrations, a way of comparing an amount of solute to amount of solution. Again, just change this. It should be ppm. It's actually, I should say, it's written in your book, um, in your data booklet, I mean, as not even ppm. It's written as the full out parts per million. So maybe let's be consistent. It's actually written fully as parts per million. Do I expect you to write that out every time? No, you'll probably just do ppm, but that is what it looks like in your data booklet. Okay, quick note on units before we get started. If we think about it and how it's given in your data booklet, is that the mass is given in grams for any kind of mass, which, while usually true, okay, again, just like with our percent by volume, it doesn't actually matter as long as they're the same. So you could have kilograms over kilograms. You could have milligrams over milligrams. It doesn't matter as long as they're the same. What you couldn't do is grams over kilograms or milligrams over, I don't know, nanograms. You just can't mix. But as long as they're the same, it's actually no biggie. Okay? Usually grams for M solute and M solution. But just like with our percent by volume, it doesn't matter as long as they're the same. Both the same. Right, so as long as your solute units are the same as your solution units, it's no big deal. All right, I won't waste much time. Let's get into it. Just remember, parts per million. What are we dealing with here? Usually, okay, very, very tiny concentrations, right? Because it's parts per million. So it's saying out of a million solution particles, how many are solute particles? And if we're counting that way, that's a good hint that, well, there must not be very many. Right? If I told you that you're 1 out of a million, that usually means you're pretty special. You're one of a kind. There is a low concentration of you amongst people. Okay, so 1 in a million is literally 1 part per million. Same thing here. Okay, so a 200-gram sample from a bottle of water contains 5.4 times 10 to the negative 3 grams of mercury. Okay, so first clue that this is what I think it is that this number is way smaller than this number. Remember, solute, there's always less solute than solution. There has to be, right? So M solute must be. Plus it's mercury. Usually with ppm, it's something poisonous, right? That's why we're so careful about it. That's why we're looking at such small concentrations. We got to be careful, even at a very small amount. So the concentration of mercury in the sample expressed to 2 significant digits is blank ppm by process of elimination, but also by the fact that this is the total thing that we're looking at. We're saying in this total thing, there was this much mercury solute. So this is going to be the mass of our solution. It's a 200-gram sample, a bottle of water. It's saying the concentration of mercury expressed to 2 sig digs is blank ppm. So what am I looking for? Parts per million. Okay, so let's write down our givens. M solution, the mass of the total solution is 200 grams. Mass of the solute, again, the solute is the thing dissolved, in this case mercury. This is a small number, 5.4 times 10 to the negative 3 grams, right? It should be small if we're dealing with ppm. The concentration of mercury in the sample is what we're looking for. And so that's our question mark. So as always, go to your data booklet. Look for the equation that has everything you're given, right? So these two, everything you want, so ppm, and nothing else. There should only be one in 99% of questions, but some are 2 steps. But even then, you can kind of get your game plan by doing this stuff, right? And looking at what equations you have at your disposal. So it is going to be our new friend, ppm equals M solute over M solution. And then times 10 to the 6, which again is just a fancy way of saying a million, right? 10 to the power of 6 is a 1 and 6 zeros, which we usually would call a million. So ppm is, in this case, a unit, right? Parts per million. Just like in our last one, percent was a unit. In our percent by volume, percentage was the unit. Okay, so now parts per million is just the unit. It's saying in a million, there's this many. So ppm equals, sorry, I should say we are looking for ppm. It's all by itself already, so no manipulation required. Our lucky day. ppm equals 5.4 times 10 to the minus 3 grams over mass of solution is 200 grams, okay, times a million, or 10 to the 6 ppm, okay? These are the same unit, so I'm okay here, right? Again, it doesn't matter what they are as long as they're the same, but grams are definitely the same, leaving me with my only units are going to be ppm. That's good. That's what I wanted, right? So this means when you do the math, you should be getting ppm equals, and again, 5.4 times 10 to the negative 3, guys, don't be scared of that. That's just a number, right? In fact, we could move the decimal now if we wanted. Let's say if you put that in your calculator, you will get 0.00543 grams over 200 grams. I know I just canceled out the grams, but forgot about this part. Times 10 to the 6 ppm. This is not a necessary step, but if you wanted to, right? If you don't like this scientific notation, you could turn it back into regular notation, okay? Just move the decimal the other way or put it in your calculator. Okay, grams are gone, and we have that. I'm just going to do this one a little bit more step by step here. So you have 0.0054 divided by 200, and that gives you, small number, which makes sense. This is a ppm we're dealing with, right? So I'll show you the reason I'm kind of doing this. We have 0.0000, 0.0000, just counting right. Yes, 27 nothings right now, okay? This is what we have times 10 to the 6 ppm. So all I've done right now is this part of the equation, okay? I've just divided those two numbers. So you'll see what I mean here. This part here, this is how many mercury, our solute, this is how many mercury particles there are for every one water particle. Do you see how annoying it would be to talk about this in this small of numbers, right? So what they say is, okay, yeah, we know it's really small for every one. We know it's really small for whatever ratio we choose. Let's just, so we don't have to use these dumb small numbers, let's say how many parts of mercury there are in a million of our solution particles. So we're going to take this and we're going to times it by, and I'm sorry that's kind of squished there, but that is just times 10 to the 6. Okay, so we're going to take that and multiply it by 10 to the 6, or a million, okay, which is going to just move the decimal 6 places that way, but it will end up giving you 27 ppm. What does that mean? It means in a million particles of this bottle of water, 27 of them are mercury particles. Okay, whether that's safe or not, I don't know. I'm not a health inspector. Sounds high, honestly, to me, but who knows? Okay, but that's where we're usually dealing with it, is things that are kind of deadly. So we don't want to, we want to be really cognizant of even very low concentrations. Okay, do the paraphrase. I have my units already. We're good. Is 2 sig digs okay? 3, okay, so maybe I have to add a sig dig, but only 2 sig digs in the mass of mercury here. So 2 is fine. So I would just write 27. That's my answer. Okay. Jump right into the next one here. So carbon monoxide, you've definitely heard of that, right? See what we're talking about with ppm. It's usually things that you don't want very much of, hence the low concentrations that we are aware of. It's a deadly gas, takes place of oxygen molecules, binds to hemoglobin in the blood. If you are smoking a cigarette, the concentration of carbon monoxide in each breath that reaches your lungs is approximately 200 parts per million. Okay, so that is our, what is that going to be? Which variable? Well, the concentration in each breath that reaches your lungs is approximately 200 ppm. So obviously that's our ppm, okay? What is that saying? It's saying that if you breathe in, if you take a million of your lung particles when you're smoking a cigarette, 200 of those air particles are going to be carbon monoxide particles, okay, let alone all the other nasty stuff in a cigarette. So the mass of carbon monoxide that would be present in a sample of air having a mass of 9.6 grams, okay, which is about the mass of one breath. So don't forget, air has a mass. It's light, but it does have a mass. Expressed in scientific notation is A point B times 10 to the negative C grams. What are the values of A, B, and C if you write it that way? Okay, so good enough. Oh, my scroll's not working. There we go. Okay, so the mass of CO, carbon monoxide. So remember, carbon monoxide is the thing that is dissolved in the air. It's the very small concentration, yes, but it is the thing that's dissolved in the air. So that is our solute. solute. And that's kind of what we're looking for, right? It says the mass of that is blank, 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 and blank. So we're looking for the mass of carbon monoxide present in a sample of air. If the air, in which case the air, remember I said when we were first talking about solutions that air was actually a solution. It has a bunch of gases dissolved in it, right? So air in this case, that's the mass of our solution, right? Remember, solutes don't always have to be solids. Solvents don't always have to be liquids. They could both be gases. So we're saying how much carbon, exactly. How much carbon monoxide is in this much air if the concentration is that in every million particles of air, 200 of them are carbon monoxide. So let's figure it out. We have ppm, we were given that, 200. Okay, we have the mass of our total solution. So in a total breath, there are about 9.6 grams of solution, being air here. And it's saying, if that's the case, then how much carbon monoxide is in that air? So, like always, go to your data booklet, page 10. You need an equation that's got all three of these things and nothing else, right? So, it's this guy, ppm equals the mass of the solute over the mass of the solution times 10 to the 6, or a million. Okay, this time we're not so lucky. We're going to have to manipulate this guy because we want M solute, right? That's what we're looking for. So we need to get it alone on one side of the equal sign. To do that, we have to undo whatever is in the way, I say, right? Whatever is stopping it from being alone. So that's these two things here in this case. It's being divided by M solution. It's being multiplied by a million ppm. Again, if we follow our reverse order of operations, our backwards bed mass, our SAMDEB, right? Backwards bed mass. If we follow that, okay, to undo stuff, then division and multiplication are kind of lumped together. It doesn't really matter which one we deal with. So I'm just going to get rid of that because it's kind of sitting out there waiting to be chopped off. You know what I mean? Times 10 to the 6 ppm. So see ya. But I can't divide this side by 10 to the 6 ppm and not do it to this side. So I got to do it to that side too. And there we go. So calm down, just write it down, right? So not calm down, but just take a breath and write what you got. Okay, you don't have to be done in one step. I know this can look worse at first, but that's only when you don't realize, hey, I just got rid of stuff. I'm making progress, right? Always look at the progress you've made. Don't think about how far you got to go still, because we really don't have to go that far. We are left with now ppm over 10 to the 6 ppm equals whatever's left on this side. And whatever's left on this side is still M solute, and it's still being divided by M solution. And we just regroup, right? Go back to where we were. Say, okay, I still want this. That's never changed. That's been my goal from the beginning. What's happening to it? Well, it's being divided by M solution, right? So that's no good. I need to stop it from being divided by M solution. So the opposite of being divided by M solution, to undo that, is multiplying by M solution. So see you later. See you later. And I got to do that to this side too. Okay, M solution times ppm over 10 to the 6 ppm. Well, let's just write down what I got. Forgive me, I'm just going to flip sides of the equation, right? I'm allowed to do that. So I'm just rewriting it so that this is now on the left side, kind of because I know where this is going, right? M solution times my concentration in parts per million over 10 to the 6 ppm. If you like, you can put this as part of the fraction, or you can keep this kind of like that. It's up to you, whichever one. This is being multiplied by this divided by this. So however if you want to say this is being multiplied by this divided by this, the way I've written it, that's fine. If you want to say this is being multiplied by this and then divided by this, that's actually the same thing. It's totally fine. Up to you. I'm going to choose to do it that way. Okay, so all I did there was just flip them around, right? Write down what I got, and lo and behold, hey, look at that. What I wanted is all alone on one side of the equation. That means I'm ready to plug in and get to actually calculating, right? Pressing the buttons on the calculator. So M solute, Oh, I don't want that color. M solute is equal to the mass of the solution times the concentration in ppm, which I believe was 200. Yes, 200 ppm, parts per million, divided by a million, or 10 to the 6, whichever one you prefer. Okay, and look what happens to the units here. Perfect. Remember, units are a free way to check your work. Take advantage of it. Parts per million over parts per million. Boom, boom. Okay, there we go. Whoops, I'm just realizing I forgot to plug in. Okay, just ignore while I plug in like I should have done in the beginning. M solution was, what was it, 9.6 grams. Sorry, okay, there we go. That's how that should always look. And the reason I noticed that is because I went to check my units. So I got parts per million over parts per million, those are gone, and I'm leaving me with the only units that are left are grams, right? So that's good, because I'm looking for a mass. And in chemistry, we measure masses in grams. I know in physics, we did it in kilograms, but in chemistry, they're kind of weird and they do it in grams. So when you do the mass of the solute, you get 9.6, right, times 200, and then divide that by 10 to the power of 6, okay? When you do all that, if you're careful on your calculator, you should get, and again, you don't need to do this all in one step. You can break it up more if you want, but I got 0.00192 grams. Okay, now this is not my final answer. This is GRASS. I have given the required analysis solution, but I need to stop, make sure I've answered the question I want, the way I want them to. And lo and behold, I haven't, right? They want it in this format, A point B times 10 to the minus C. Okay, well, that's okay. That just means I need to write this in scientific notation. So the decimal is here. It just needs to go after the first number that's not a 0, right? After, the first number that's going to make this be a thing between between 1 and 10 when all is done, right? So that would be 1.92. So 1, 2, 3. Okay. Now, that means I have how many sig digs? Oh, 2 sig digs. Okay, so the 2 is extra. So to 2 sig digs, 1.9, and that's actually good, right? I don't change the 9 to a 0 and then round that up to a 2, because the next number after the 9 is a 2. So it stays as a 9. 1.9 times 10 to the power of, now I moved the decimal 3 times, but this is a small number, right? This is not a big number. This is a number smaller than 1. So it's times 10 to the negative 3, right? What does that mean? It means we took 1.9, we divided it by 10 once, we divided it by 10 twice, and we divided it by 10 3 times. Don't believe me? Take 1.9, divide it by 10 3 times, and you should get this exact thing on your calculator, okay? 1.9 times 10 to the negative 3 grams. So if I write it the right way, it's saying when you write it this way, what are A, B, and C? So A, B, C, and looks like A is 1, B is 9, and C is 3. So what would I write? 1, 9, 3. Okay, so again, I will put some whiteboard practice up. I apologize. Those actually shouldn't be in your notes, but that's okay. That works out for you. You can just do them in your note booklet there. Here are some whiteboard practice ones I would normally get you up to do. Make them a bit bigger so you can pause the video, try these out if you want. All the answers are here as well if you would like the extra practice kind of concentrations mixed examples that would normally be an assigned assignment, but times are different now, so it's there if you would like. They have all the answers available as well. Okay, these are good practice as well as those ones. So that wraps up parts per million.